Memory management in Java. I know it's dull and boring, but I'll try and make it as interesting as possible, right? So disclaimer, I'm not an expert at this topic. A few years ago, I encountered some issues with the application that I was working on, and then I had to deep dive. And when I did, I realized how important it was to understand how the JVM's memory model works. And then I was able to make informed decisions. So all I'm going to do today is actually share that experience. And to do that, I'll have to start with some very basic terminologies. What is garbage collection? So garbage collection is the process of removing objects from the heap that are no longer used. There are two types of objects, reachable objects and unreachable objects. So reachable objects are live objects that are being referenced by at least one other object within your application. So if you can imagine, there's an object that's referenced by another object, which is referenced by another, and so on. If you traverse through all these references, you will reach the root node of your application, which pretty much creates the object graph. On the other hand, unreachable objects are objects that are no longer referenced by any objects in your application. There are three main or basic steps in garbage collection: mark, sweep, and compacting. So mark, the first step. The garbage collector starts from the root node. It traverses through the entire object graph, visits every single node, and marks every object as either reachable or unreachable. The second step, sweep. Now we know which objects are unreachable. The garbage collector will then delete all these unreachable objects from the heap. Then compacting. So once the objects have been removed, you can imagine gaps in your heap. The process of compacting is very simple, just arranging all these objects in order to allow for contiguous allocation. So these are the three main steps. Now, let's look closely into what our JVM's heap memory looks like. The JVM's heap is divided into two main spaces: young generation and old or tenured generation. The young generation is further divided into Eden space and two survivor spaces. Eden. So the name comes from the theory of Genesis in Bible, where the Garden of Eden is the place where life was first created. So therefore, when new objects are created in Java, when you use the new operator, when you say new hash map or new array list, the object is allocated in the Eden space. Now, let's look at some animation. Let's see how it actually works. Let's see the heap memory in action, coming alive, right? So I've zoomed in to the young generation. We're going to look into that first. So as I said, we have the Eden space, we have survivor space 1, and we have survivor space 2. When a new object is created, the object is allocated in the Eden space. I've represented that in green. So more objects are created, they get allocated in the Eden space. So while your application is running, one or more objects will become unreachable, right? That I've represented that in gray. Now you can see the Eden space is full. Now a new object gets created, but the allocation will fail because the Eden space is full. This is when a minor garbage collection kicks in. So that runs across the young generation. So when that happens, the reachable objects are moved into the survivor space 1, whereas the unreachable objects are removed from the heap. Now, you see a number on these objects. Number 1, what does that represent? That's telling you that these objects have survived one cycle of garbage collection. Now, more objects are being created. They get allocated in the Eden space, as before. And one or more objects have become unreachable in the Eden space and in the survivor space. Again, a new object is created. At this point, the allocation fails. Therefore, another minor garbage collection kicks in. Now, the reachable objects are moved from the Eden space into the survivor space 2, and this is why we have 2 survivor spaces. Now the objects from the survivor space 1 are also moved into survivor space 2. The unreachable objects are deleted from the heap, and if you see there, the number has changed again. What that means is the last 4 objects have survived 4 cycles of garbage collection, whereas the other 5 have survived 1. Now, how long is this going to happen? Like, how many times will this happen? So that's where we have something called as an aging threshold. So for this purpose, for this talk, let's say the aging threshold is 8. So when the objects reach the aging threshold of 8, like, what does that mean? That means if they survive 8 cycles of garbage collection, then they get promoted to the old generation because they are no longer young objects, right? They're long-lived objects. They've survived so many cycles of garbage collection. So they get moved to the old generation. Now, the big difference between young generation and old generation, as the name suggests, young generation is for young objects, for short-lived objects. And what that means is minor GC will happen within the young generation. It happens only across the young generation. Therefore, it will happen more frequently and it will have less pause times. Whereas the old generation, a major garbage collection kicks in. That will happen across the heap, from young generation all the way to the old generation, right? That will take longer, therefore longer pause times, and fewer, it happens frequently. Less frequently, right? So hopefully by now you have some overview of how the JVM's heap memory model works. We all know Java looks after memory management, handles that automatically. Then why do we even need to understand how this works? This is probably where the case study will come in handy. So I told you a few years ago I worked on an application. It was a Java service written in Java 8. It was a very simple service, wasn't doing anything complex. Then we started to see a hit in latency. We're seeing some issues. So we looked at various things to see what's going on, what could be the cause. And amongst other things, one of the things I wanted to monitor was the memory. So this is a snapshot of the memory usage of the application. We were using the CMS garbage collector, which is the concurrent mark sweep garbage collector. You can see 2 graphs there, one in green and one in blue. So the green one is the memory usage of the Eden space, of the young generation, whereas the blue one is of the old generation. So you can see in the usage of the Eden space, the dips that you see are where minor GCs are triggered. So you can see that they are happening frequently. That all looks quite healthy, so it all looks fine. But what was interesting and a bit puzzling to me was, why is there a high usage of the old generation? That doesn't make sense. And why doesn't it make sense? Because I was a big fan of immutability. Well, I still am. We were creating a lot of short-lived objects, right? So young objects. So which means that obviously they're supposed to be in the young generation. They will soon become unreachable. So they should go through lots of minor GCs, which means, it should happen more frequently, and the usage of the Eden space, the young generation, should be a lot higher, and it should probably not even reach the old generation, or maybe a little bit, but not such a high usage of old generation. So it didn't make any sense to me. So I started looking into it, and I was thinking, what was happening? So because of the immutability craze that we had, what we were actually doing is we were creating lots and lots and lots of objects. And the other factor was that the CMS garbage collector had a fixed young generation size. Yes, you can provide, you can tune it by saying, well, I'm going to give a ratio. I'm going to say I want 1/3 of the heap memory to be young generation, whereas the 2/3 to be the old generation. But it will still be fixed, right? So with the combination of the two, creating lots and lots of objects, now look back at what I took you through. If you imagine the heap now and the Eden space, we're creating lots of objects. The heap, the Eden space becomes full very quickly, right? Even though they are short-lived objects, they don't become unreachable by the time, because we're creating so many objects, and so they get moved to the survivor space, and so on. And what happens is they start surviving lots of cycles of garbage collection, and quickly they reach the aging threshold. And therefore, even though they are short-lived objects, because of the number of objects we were creating and because of a fixed young generation size, they moved into the old generation. And when we go to old generation, the GC is not going to be frequent, it's going to take longer, and therefore this issue is happening. So how did I fix it? What did I do? So as I said, this was a Java 8 application, right? So at that time, G1 garbage collector was not the default. It became the default from Java 9. So I started looking at G1 and was exploring what that looks like and how that works. It was new to me at that time. So G1 works quite differently to the traditional garbage collectors. So G1 is one memory area which is divided into multiple regions, almost like 2,000 regions, right? And the spaces, the regions, were mapping logically into Eden space, survivor space, and old generation. There's a fourth type of region, which is called the humongous region. For this purpose, I'm going to leave that out of the talk. We'll just focus on the three regions, right? The key difference, or the one that really attracted me, was that young generation in G1 garbage collector can be dynamically resized. So, which means when I'm creating more and more objects, more Eden spaces, right? So more objects can be allocated in the Eden spaces. And also, before the next garbage collection, what happens is that it will calculate the size of the Eden space, the size of the survivor space, based on the usage of your memory. And then it will resize automatically, either make it smaller or make it bigger. So if you think about using G1 for the issues that we are having, if you try and link that together, the problem we had was we were creating too many objects and the young generation was fixed. Now the young generation can be dynamically resized, and therefore the objects can be placed or allocated in as many Eden space as you want. That means the short-lived objects will stay in the young generation and they will go through minor GCs, and that will be quicker. The other thing I found out about old gen in G1 is that it uses a much faster algorithm called the snapshot at the beginning for the marking phase. And also it compacts on the go. So what that means is we talked about the different steps of garbage collection, so which was sweep, and we talked about, what was the other thing? Mark, sweep, and what was the other one? Sorry? Compact, exactly. I'm just checking if you guys are listening. Cool. So what that means is while you're sweeping, it's also compacting. So it's doing them together. So you're saving time, right? And you can also change the pause time. You can regulate the pause time. So we also have reduced pause times. So as I said, it was not the default garbage collector at that point. So I had to make some changes. What changes did I make to my application? The only thing I had to do was that. Just say use G1 GC. And then I gave it a go and saw how it's going to work. So I now have a resulting snapshot. So you can remember the green graph and the blue one on the left-hand side was the old one using the CMS garbage collector. And then you can see the new graphs. That is using the G1 garbage collector. The light blue graph is the usage of the Eden space. Now you can see how healthy that looks. The usage of the Eden space is very high, as expected, because that's what we want to see. And you can see more frequent minor GCs happening. Perfect, right? And the red line, you can see there, is the memory usage of the old generation, which is quite low, as expected. So I was very happy. So was my manager. So the takeaway, whatever language you use, it doesn't matter, Java or whatever language you use, it's always useful to understand how memory management works. You might never have to tune it in your life, maybe, but when you do have to, it's better to understand how things work because you will be in much better position to make informed decisions. You don't have to guess, you don't have to make assumptions. You'll actually know what to do, right? And I'm not saying G1 is the best. It's now the default garbage collector. And then we do also have the Shenandoah, which is coming up. So that's also good. I'm not saying it's the best, but for this use case, for the problem that I was looking at, for my application, G1 was the best fit, right? And with this exercise, actually, I realized that memory management is not as boring as I thought. It was actually fun to learn about this. So choose the right garbage collector for your needs. Thank you.